All right, so example 2, represent the RLC circuit with a system of differential equations. And before I actually give you the circuit, I'm gonna tell you what all the components are and like what they look like in it, so you don't just see it as a mess of squiggles. So first we're gonna make a table with component, the symbol, and the voltage drop. And our first component is going to be the inductor. And its symbol is kind of like this little bumpy thing. For some reason, the book always draws it with 4 bumps. I don't think you have to do that, but if you want to be consistent. And then its voltage drop is going to be L, which is just a unit for the value of this inductor. I think it's L henries. Henries is the unit. Actually, yeah, L is the abbreviation for henries, which is the unit, because Henry starts with an L. So its voltage drop is going to be the value of the inductor times the time derivative of current. And our second component is going to be the resistor. And its symbol is this kind of zigzag. And its voltage drop is going to be our number of ohms times just current by itself. The third component is going to be the capacitor. It's going to be kind of this little railroad track thing, and its voltage drop is going to be inverse capacitance, so that's 1 over C times charge. And our fourth component, the battery, which is really just any voltage source. It could be a battery, it could be anything pretty much. It's labeled kind of this alternating long and short line thing, and then you want to label it with a plus and a minus. And that voltage drop is going to be negative electromotive force. And the reason for this is that you can kind of think of what the battery does, which is put voltage into the system, as a negative voltage drop. Like it's pretty much a double negative, so it cancels out to be a positive, if that makes sense. And a couple more things before I give you the circuit. We're going to need Kirchhoff's laws of voltage and current. So the first one is his law of voltage, which states that the sum of the voltage drops in a closed loop circuit is always 0. And this is going to be the main thing that we base our differential equation on. This is how we're going to set it up. Very similarly to how we use Newton's law to set up the differential equation for the spring problem. And we need one more, Kirchhoff's law of current. And pretty much what this says is that current splits at a junction. And what this means is that if you have a junction in your circuit, so let's say current is traveling this way, and then it splits off into 2 different branches. Let's label it current 1 and current 2. The total current, just I, is going to be equal to the sum of I1 plus I2. And then you can keep saying this for however many currents you have. The law is always going to apply. And so now that we have all this stuff, oh yeah, make sure to memorize all this stuff. This is very important. So now that we have all this information, I can give you the circuit, and you're actually going to know what it means. So going to start by drawing a battery on the left-hand side. Then on the top, whoops, plus, minus, I'm going to draw an inductor. And that's going to split into a resistor going down. Trying to draw this stuff nicely. And then on the top, it's going to go into a capacitor. Then go down to another resistor. And then these are all going to connect back up to the battery at the beginning. And so let's put some units on this. So the E0, the voltage of this battery, DC, so it doesn't change, is going to be 100 volts. And this inductor will have a voltage L equals 2 henries. This resistor, let's call it R1, is going to have a resistance of 50 ohms. This capacitor is going to have a capacitance of 0.008 farads. This resistor R2 is going to have resistance of 25 ohms. And that's really all we need. So if you recall back to 3.7, pretty much how we found the differential equation was by using this general form, Li prime plus Ri, just 1 over C times Q equals the electromotive force. And so pretty much the derivation for this comes from Kirchhoff's law of voltage. So if you move this electromotive force term over, that gives you this equation. And then you can kind of see how all these terms, which is equal to their voltage drops, is all summing to be 0. And so this is really the derivation of these differential equations. And how you want to do these is over loops of current. And so it doesn't really matter which direction your loops go in, as long as they're consistent in your circuit. So you can't have like one loop going clockwise here and one going counterclockwise, because then your numbers are going to be messed up. So pretty much how we're going to approach this is we're going to start by picking a direction for current. Let's just say clockwise over the entire thing. So that also means that the current is going to travel clockwise in any one of these loops. So let's call this loop current 1, and this loop current 2. And before we start setting up the differential equation, I'm going to note that the current here splits into 2 parts. That's Kirchhoff's law of current. So if you have I here, you're going to have I2, this current here, and I1. And then note that these currents are traveling in these directions, in the same direction as their loop. And that's going to be pretty important for when we set up the equation. So getting to the equation, let's just start with this first loop, I1, at the very top with this inductor. So we look back here, the voltage drop for an inductor is going to be the value of the inductor times di dt, which is just going to be 2 farads, not 2 farads, 2 henries times di dt. And then now let's go to the resistor. And this is a bit more complicated because instead of having the total current, like, make sure this is I sub 1 because it's in this loop. Instead of having the total current, like we did here, we have split current. Oh, my bad. The current here for this inductor is just going to be I1 because it's in this loop. So that's all you need to keep track of. The variables will sort themselves out because of how the math and current works. So for this resistor R1, we know that has a resistance of 50 ohms. And then when we're trying to find what current to multiply this by, it's kind of difficult because we have I1 traveling this way. But then if you look here, I2 actually wraps around, and because of how this loop works, I2 is going to be coming up, this way. So it's actually going backwards in the resistor. And then pretty much what this means is that this resistor, at least for this loop, is going to have a current of I1 traveling this way minus I2 traveling this way. And then for our battery, we're going to take the negative electromotive force as our term, so minus 100. And then we're just going to set this all to be equal to 0 because of Kirchhoff's law of voltage. Everything, or all the voltage drops equals 0 in a closed loop circuit, which we have here. And so for our second loop, I2, we're going to start with this capacitor. 1 over this, as you can see, inverse capacitance times charge is the voltage drop. So 1 over that number is 125 times charge. And make sure to label this as charge 2 because charge and current are related. And this is current 2. And then we're going to add the resistance of this resistor, 25 I2. And then for this resistor, we're going to do a very similar thing as we did for it in loop 1. So it's 50 ohms resistance. And so since we're now finding the equation for this loop, we're going to consider this direction as positive clockwise, which means that instead of I1 being positive going down here as it was in this loop and I2 being negative, it's actually flipped because it's traveling in the reverse direction. So that's going to give us I2 traveling in the positive direction minus I1 traveling in the negative direction. And then since we don't have a battery at all in this loop, that's all the components, and we don't need an electromotive force. And so this is our system of differential equations for this circuit. And the solution would come in a pair of I1 of t and I2 of t. And then that would just tell you the current through these equations during any t value. And so for these examples, we left one from the book out. It was on brine tanks. And really, it's very much the same process. Like if you go back to section 1.5, I think it was, and you look at the law we derived for how the flow works, you can pretty much apply the same thing where you just like plug in all the terms just with different variables, and then it'll produce a system of differential equations. So if you want to do all that, feel free to go through the book and mess around with that. But beyond just these examples, it can apply to so many different things. Like the particle example I mentioned previously, there are really limitless applications to systems of differential equations, which is why I think they're so cool.